The direction of the Earth's rotational axis is fixed in space as the Earth revolves around the Sun, only approximately. It actually moves by just over 1 degree over a century. And the reason for that is that the Earth's rotational axis precesses. And I'll explain in a moment what I mean by this. Okay, so everybody is familiar with the precession of a top, right? If I have a top and its spin axis is vertical and I start the spin, it will stay vertical for a while, but then there's a certain amount of friction at the point of contact, and there could be a disturbance created which would cause actually the rotation axis to tip away from the vertical. Then the laws of physics tell us that basically the resulting motion would be that the top would still be spinning, so it would still be, the disk would be, the top would be still rotating, but its spin axis would also be rotating itself. This motion is called precession, right? So if this is the rotation axis of the top, by precession I mean this, that it's revolving around the vertical direction. Well, it turns out that the Earth's rotational axis is doing the same thing. And the reason for it is, in this case here, what is happening basically once the top is not in the vertical direction, the gravity is trying to pull it down. But so-called conservation of angular momentum, the tendency to preserve this rotational motion, makes the top still spin. And the combined effect is that the top would be spinning and at the same time precessing around the vertical direction. In the case of the Earth is not perfect sphere. It is slightly fatter in the middle, around the equatorial plane, okay? So basically there is a gravitational pull by the Sun and the Moon that is trying to set its spin axis straight, right on, so that it's vertical to its orbital plane, right? So this is to the Sun. So the gravity of the Sun is trying to actually straighten this rotational axis. And the combined effect is that the Earth's rotational axis is precessing around the vertical to the ecliptic, and it turns out that it will make one complete round trip in 26,000 years. Okay, so let's see how much it moves per century. I have 360 degrees in 26,000 years, right? That is 360 degrees in 260 centuries. And that's about 1.4 degrees per century. So indeed, as I mentioned at the beginning of today's lectures, as the Earth revolves around the Sun, it approximately maintains the same direction of its rotational axis, at least on the time scale of several generations, okay? But actually, there is a shift of about 1.4 degree per century, so that it makes a full revolution of 360 degrees in 26,000 years. One consequence of that is that actually, right now, so that basically what the consequence of this is that the North Celestial Pole would be making a circle on celestial sphere. So this is where the North Celestial Pole is right now. And there happens to be a star, Polaris, or the North Star, very close to it. That's the star in the handle of Little Dipper, right? And you get to it by extending the line from two pointer stars in the Big Dipper, right, to get to the North Celestial Pole. But that is now. In 14,000 AD, as the North Celestial Pole actually moves because of this precession of the Earth's rotational axis, the star closest to the North Celestial Pole in 14,000 AD would be star Vega. In the past, at 3000 BC, roughly at the time when Egyptian pyramids were starting to be built, also the Stonehenge in British Isle and many other circles of stones there, the star that was closest to the North Celestial Pole was Tuban. Okay? So only right now the Polaris marks the location of the North Celestial Pole, the point directly above the Earth's rotational axis. But as the Earth's rotational axis precesses about the vertical to the ecliptic, the North Celestial Pole, the point above the Earth's North Pole, would be moving among the stars. Right now it's here. In 14,000 AD, it would be here. In 3000 BC, it was there.